You told me it's not going to happen unless there's like these guys who want it.
Okay, we're going to get started, and we're doing a little bit of like simultaneous learning and experiments today because some of the experiments take several minutes for the thermometers to come into equilibrium with the environment. So we're going to be learning about the psychrometric chart, and we're spending a whole lecture on that today because I know how much you guys hate reading charts, and there are a lot of problems that arise when you don't do it correctly. So we're going to learn how to do it so that you feel very comfortable, confident, you know how to use the chart, and you know how the chart translates into the real world if you were to use the equations that the chart is based upon. So we're going to do some temperature measurement today. We're going to do measurements with the wet bulb, with the dry bulb. We're going to calculate the humidity of the room and compare it to the value that's given on this thing. I don't trust this to be super accurate because it was like $4. So as long as it's close, hopefully we'll be able to do that. So we're going to get the experiment set up, and then we're going to talk about the psychrometric charts, and then we'll come back to the experiments and see kind of how the data is going. So let me just, I guess, show you what we're using today. This is just a cheapo alcohol thermometer, like a $2 thermometer from Walmart. So we're going to use it just to throw it in there and see how it works. This is a very expensive alcohol thermometer that if it gets broken, I will be very upset. So please be careful of it. It's going to be a lot more accurate. This is probably what we will use as our control or our actual value and compare all of these others to it. These Thermo pens are also a little bit expensive, and they're not generally made to do wet bulb, dry bulb experiments. They're made for measuring internal temperature of food products. But they do give a pretty accurate reading of temperature, so we'll do the experiment with those as well. And then these are just little fans that we'll use in the wet bulb experiment. So basically what we do is we will use these thermometers to take a dry bulb temperature measurement in this room, so we can get the temperature measurements off of here. We can get them in Fahrenheit or in Celsius, either one. I think this thermometer only does Celsius. Yeah, these are dual thermometers, so they're real fancy and great. I can switch one of these into Celsius as well. So once we've got the dry bulb temperature, then we will use a wick that's been soaking in room temperature water. I left this out at room temperature for a couple of hours, so hopefully the water is the exact same temperature as the air temperature in the room. If you were to do it with water that was a different temperature, it would skew and alter your results. So that's part of the experimental setup. And then we'll have the fan just blow onto the bulb, and after it comes into an equilibrium state, usually about 5 minutes or so, then we'll take that temperature reading, and that will be our wet bulb temperature. Okay, so we'll have these maybe distributed around the room for dry bulb measurements. So if you want to take one, look at one, and figure out what the temperature is. We're going to do several different experiments, and I do have a container of water with gauze outside too, so if we want to try to replicate this experiment outside, then we can try to see what the outside humidity is and compare it to the indoor humidity as well. So who knows how accurate these are all going to be, but it's fun sometimes to put these into application. So does somebody have a quarter or a nickel or penny? Or maybe a dime. Okay, so I'm going to change this measure in Celsius. I have to do that by, forget. upstairs. There's one of these things I have to switch, but I don't remember which one, so I'm gonna mess with it right now. Yeah, they're all measuring Fahrenheit. That's fine. We know how to do that. Just use this as our Celsius one. Okay. So the thermopens are all reading slightly different temperatures. What temperature do you have? And who wants a thermometer and try to read the temperature off of it?
I don't want to touch it. You might touch it. You look at it.
I'm not gonna touch it, just take it.
You look at it, but you might get sick. Maybe you've got 2 minutes.
All right.
When you handed me that one, it was 78 and a half and it dropped to 76.
Okay, so don't touch the bulb as you're measuring the temperature or the probe, right? Because then what's it going to measure? Your body temperature. Okay. So we're trying to get these into equilibrium, let them just sit there and get a correct and accurate temperature. And then whichever device you're using for your temperature measurement, just write it up here in this top column. So if you're doing your experiments with the thermopen, or if you're doing your experiments with the alcohol thermometer, or whatever value you want to use, even if you don't have a thermometer in front of you, you'll share with somebody next to you and get those values. Okay, so write down T1, which is the dry bulb temperature. And on this,
We can use Celsius.
this one is 22.5 Celsius.
Yeah, 47. Nope. 27 Celsius.
I got like a 68.1.
What is that?
Thank you. Here you go. What's that one called? A caliper?
You have an extra.
What's that? What's the number? 74. Celsius.
Okay, so then using that temperature, whether you're in Celsius or Fahrenheit, make sure you write down the correct units. You go to your table in the back of the book and interpolate to find your saturation temperature at that, saturation pressure at that temperature. So PG1, and then you'll also look up HG1 at that temperature and pressure.
Which table is it?
Which table do you use?
Oh,
Depends on if you're in the SI unit or the English unit system. So you need to look in the water table. You're finding PG, so the saturation pressure at the temperature that you determine from your thermometer. And then you also need to find H sub G.
Okay, so now for HG, yeah, it's 25 and 30, and for 25 it's 2,526.5. Okay, it's HG.
oh, 2,550. Are you taking the wet bulb temperature right now?
So I'm taking a wet bulb temperature of this thermometer. Your wet bulb temperature for your thermometer needs to be done with your thermometer. So I have these wicks up here. You'll need to wrap the bulb with the wick, and I have a toothpick so that you can actually stick it in there. And then you'll set it up in front of this fan, and then we'll take the temperature measurement. Okay, so you're gonna have to use the toothpick to turn it around.
Yeah, it's just fine and then gang of 6.
Okay, so can you turn it out so that you can the water?
I don't know if it was out or not, but they said there was one I got that you had to use gang of 6 stuff.
Just sign up for the web.
If you look at the 325, you'll see that.
That's just the answer.
It needs to continuously wick moisture.
I think.
All right, so now we've got these set up. We'll just wait.
7.4.
Okay, don't stab yourself with that. Problem with this one though is it.
For pressure, I got 0.42214. And then for HG.
Okay, so we're gonna come back to these experiments, but we're gonna continue on and talk about psychrometric charts and learn how to use them. Because previously, as we've talked about many times before, you can take any two independent properties and specify all the rest of the state of that material. Well, the same thing goes for specifying humidity or specific humidity, relative or specific humidity, that you can just, in order to determine the wet bulb temperature or to determine the enthalpy or the specific volume, you just need to know 2 points so that you can use the psychrometric chart and determine all of the other property values of the air-liquid mixture at that particular state. So psychrometric charts have taken these calculations for omega, for relative humidity, for enthalpy, for specific volume, and they've plotted them all together on one chart so that if you know any two of those properties, you can find the point and look up all the rest of them where you are on the chart. So let's just look at a psychrometric chart, and everybody should have been given 2 copies. One is in English units, one is in SI units. So from your book, this is just a little bit easier because you can write on this one, and we'll do a few examples today where we're required to write on it. So if we look at a psychrometric chart, we can see that there's really a lot of different lines on here, and it's a little easier to see in this version because some of the lines are green. I don't know if you can see that very well or not. But let's just explore and see what are the different functions and properties on this chart. So first of all, if you look down here, the very bottom axis is the dry bulb temperature. So you can see it goes from 0 to 50 along the bottom axis, but it continues up the y-axis all the way to 120, and this is in SI units, so it's 120 degrees Celsius. So depending on if you're from 0 to 50 degrees or from 50 to 120, you'll be in a different position on the chart. The next one we want to look for is the wet bulb temperature. And you can see that the lines of wet bulb temperature go in a diagonal fashion from left to right or right to left, depending on how you're looking at it. But the wet bulb temperature is this dashed or this dotted line. So you can read the wet bulb temperature here, 25 degrees Celsius. If I cover it, 25 degrees Celsius is the temperature of that line. Or you can start here at 25 and you can count down 24, 23, 22, 21, 20. See, it matches up there. 19, 18, 17, 16, 15. It matches up there. So the wet bulb temperature is given on this left axis, but the lines are these little dotted lines that run diagonal across the entire diagram. Okay, the next one we look at is saturation temperature. And the curve of saturation, the saturation curve, is here. And do you remember what that line represents? What is saturation? The term saturation, what does it mean? Wet, okay, fully saturated. Yeah, it has all the water vapor it can hold. So any point along this line will be at 100% relative humidity. And we'll look at those in a minute too. So the saturation curve is on the left-hand side. That tells us if we're on that line, or if we're close to that line, we're either at 100% humidity or very close to 100% humidity. Okay, and again, the saturation temperature, you read them from the same numbers that you would read the wet bulb temperature, but this line is curved, whereas this line is straight. And you'll notice that it's not a linear relationship in the distance between these lines. So the distance from 5 to 10 is 5 degrees, right? But look at the distance from 20 to 25 or from 25 to 30. But the distance increases the further up the chart you go. Okay, so those are the temperatures that you can read off the chart. Saturation temperature is also sometimes referred to as the dew point temperature. So if you're trying to determine the dew point temperature, you would look at the point of saturation. And we'll do examples on that so you see how that works. Okay, so the next thing we want to look at is the relative humidity. So these lines that are green and they go kind of curvy like this, those are the lines of relative humidity. And you can read on the line itself what percent humidity. So it's 10%, 20, 30, 40, 50, 60, 70, 80, 90. And then again, the line of 100% humidity is the same as the saturation line. Okay? We can also look at specific humidity or the humidity ratio. That's on the right-hand side. And we read those numbers here, 2, 4, 6, 8, 10. But notice that its units are in grams per kilogram of dry air. So 10 grams per kilogram would be equivalent to 0.001 kilograms per kilogram, right? Kilograms H2O to kilograms dry air. So make sure that you make that conversion if you're using this chart to find the humidity ratio omega. Okay. The next thing we can look at is the specific volumes. So those are these lines here. And you can see that this is 0.92, 0.90, 88, 86, 84, 82, 80, 78. Okay, so the specific volume is in meters cubed per kilogram of dry air. And then the last thing that we can get on this chart, there's really a lot that we can take from it, is the enthalpy. So the lines of enthalpy are these darker lines here. And you can see that they extend up to the saturation line, but it's only the bold lines that extend through the space, just to minimize how much is on this chart. So if your point is somewhere around here, you have to extend over, following the line parallel, to see where it intersects either on this side or on this side, and then read the enthalpy from those values there. Okay, any questions on the things that are on this chart? Okay, so we have dry bulb temperature, wet bulb temperature, relative humidity, specific volume, enthalpy, saturation temperature. Did I miss one?
What's the lines going like this way, like?
That doesn't help.
Hold on. So like from the bottom point there to the right, 50 on the very bottom, the
Okay.
line going at an angle
This line?
towards the word saturation temperature.
This line.
Yes. What are those lines?
Okay, those are the lines of enthalpy.
Now, and on the very bottom, do you measure it based off the tips of those hash marks? Or like,
Are you talking about for the dry bulb temperature?
yeah,
So the dry bulb temperature, it would be like this is 20, this is 21, 22, 23, 30, 31, 32,
Okay.
33. Those other additional hash marks are to help you determine maybe, like if you're trying to figure out what the wet bulb temperature is, that it just is an eye place for you
okay.
as you're following parallel to the wet bulb temperature lines or the enthalpy lines, that it just gives you another way of eyeballing it. Okay, so pretty big and complicated, but I think you'll find that it allows us to do some pretty great things. So while we're thinking about it, let's go ahead and look at our thermometers. I think they've come into equilibrium. So Hunter, do you want to come up and read your temperature on your thermometer?
Celsius.
Okay, what did you have to begin with?
27, I think?
Yeah.
Okay, and then this alcohol thermometer, the dry bulb temperature was 22.5. And the wet bulb temperature is 17. And then the thermopen. The dry bulb temperature on this thermopen was 73, and the wet bulb temperature is 62.2 degrees Fahrenheit. Okay, so now that you have those values, go ahead and find your enthalpy values, and let's calculate also the specific humidity and the relative humidity using the equations at the top of the page. So we'll just take a few minutes break in the lesson for you to find those values.
Sorry.
What did you say the
This alcohol thermometer is 22.5 and 17. Yeah, Celsius. I'll take that back, Mr. Blake.
I don't know if it's working anymore.
Goodness.
Gotta go all the way up.
Oh, okay.
Broke it.
You want us just to do it for the two thermometers, or do you want to do it for that other one there too?
I want you to do at least 3.
Okay, what was the temperatures on the meat reader?
Stick that thermopen,
Yeah.
the meat reader. That one's in Fahrenheit. Here, I'll write them up here. So the alcohol
So 27.
was 22.5 and 17. Thermopen is 73 and 62.2 degrees Fahrenheit. And the AccuRite, AccuGraph, is that what you said? 27 and 19. Yeah, so you got some interpolation to do. And then after we do these equations, and now that we're learning about the psychrometric charts, we're also going to look up the values on the psychrometric chart as well and see how they compare.
So just keep going down through the R's. Pressure is 1.7.
Yeah.
62.
Where's your interpolation, Mr. 90?
We got, found a picture.
Yeah, you're
I just have like big
Isn't that one?
27. Start here. Then where's it? 19. I did not think that was funny at all.
I was rolling sugar.
I was like, this is sounds really dumb.
This is some beautiful.
This one.
Yeah.
Yeah.
Get it to the paper.
No, that was the other guy. Yeah. It was the first.
Yeah.
Evan, you were a fan
I thought he
of
was like
hard
that.
right now.
It's
You're like so
in that
blinded
the can is attached to the
love that you can't see logic.
Because we're
You're talking shit about jumping
Yes,
pieces.
fuck you guys. Typically, you have a piston engine on a carrier.
I'm not Dr. Wayne.
A large posterior catheter through into
I love it.
cylindrical slot.
Thank you, Patrick.
Gotcha.
Yeah, I was staring at mine.
That's fine. What was that,
I don't think it's the exact same answer as 25. Have you done alcohol one yet?
I got the very first one. And
And then you just like stop, you just like,
I was like, took the first process.
First,
I interpolated the same HG for 25 as it is for 22.
you just put in what temperature and then pressure. Where'd you get all that? You don't need to be there. 2, 4, 5.
25, 46.
I'm a bum.
What'd you get?
I don't have a book. Well, after
I don't know how I did this.
There's PDFs of
I
it.
must have something.
Keep them saved.
you should hit me up with those. Are they on the internet?
Everything's on our end.
I mean, I did everything right, so.
Because this is.
Again, I have everything right.
It's not negative. If that makes sense. Think so.
Sure.
I'm gonna listen.
I was almost so sure it was negative.
Those are negative.
All right, has anybody calculated humidity yet?
Right.
There?
Okay, that's just
So which one? Same one?
I did another interpolation around the same value is like,
I don't have to put
like look at this, like, I'm doing my interpolation, and I'm getting the same answer as like the first number up here.
Are you using the megalodon problem?
No, G3 is doing the double after that junction right there.
Yeah.
Because he should have put that coming out of a summing.
Yeah, not bad.
Look, your computer, look up the interpolation for it. It's like a million.
Here we go.
Like that.
This is good. That's Do you want to borrow here?
This has been on the second.
All the same
Previous lecture.
This is just green damping thing, right?
You can find a sensitivity. Yep, you'll agree. The formula sensitivity of this, that follows our general, that standard form.
Right.
So use that standard form.
Why did you let me do this?
So there's your A is equivalent to the great question. The two, there's side, what is the side?
Yeah, what are the?
Two squiggle them.
Yeah.
What did you get for the? I still got looking at the page.
That's the sauce.
Yeah. That's what.
Yeah. What'd you get?
2541.95.
Yeah, what'd you guys make? Yeah, mine doesn't. Mine doesn't make sense.
I know it's right.
Which one is right?
Which one did you guys get? There we go. Found the proper table. You're right. I just wrote it down wrong. Earth shattering discovery right here. I just assumed it's the same problem from the last time. There we go. I found them, man. Good.
You can see it from here. Here.
We did not beat us in my area. So it's not beat us. No.
Did you get the picture of the table I sent you?
The Jags seafood.
So, are we supposed to use these formulas on the paper to find the humidities, or we use the chart?
The formulas, because you haven't learned how to use the chart yet.
Yeah, that's why I was asking.
They should be.
It's gonna be a really boring lecture if anyone tries to watch it.
A lot of fast forward.
I'd pause it, but then I'll forget to start it again.
So, crap, man.
Let's do it together.
No.
So 27, 22.5.
Hey, you guys got cancer now. That's all you do.
What do we use? What's PG1?
I don't know, sometimes between
P2
class,
is
Your eyes are.
Yeah, I know.
the atmosphere.
Glasses.
Yeah, it's just 100 pascals.
And then I like look at lunch in the back and bring it, so it sucks.
Like the signal just kind of started getting worse and worse. Just hit the
Chick-fil-A.
Oh, Chick-fil-A.
Okay, how's it going, guys?
How do you find PG1? Like, cause like, it's just P, like.
You just sit tight, Blake.
Okay.
So the temperature that you found at T1, right, so the dry bulb temperature,
Mhm.
if you go to the property tables, you can find a saturation pressure that's associated with that temperature. That's your PG1.
Oh, okay. So it's not like a EF of PG.
It's the same.
It's the same thing.
Also the same thing.
The saturation, it's along that line under the dome. Right there's a-
Is for omega 2, is P2 just atmospheric pressure?
Yeah.
Never just hold this
It's a new discovery here.
What's atmospheric pressure? PSI.
And PSIA is 14.696. What's GD? Oh, B. I still have to interpolate and find all the property values. Okay, so how are you doing? How far have you gotten on your,
We got our,
I'm doing the UIDs.
we got 85%.
for which one? Which one did you get 85?
Walmart Thermo.
No,
That's way too high.
yeah.
Screwed up that.
It should be about 48%. What did you get for your, I guess I'll just load it.
I didn't know really. You have to interpret everything.
Because you.
I just turned the thermostat up to make it 25.
Tell me after you guys finish. For air.
This is the one I got from that girl in the library.
It's in your book.
It's kind of sketchy. No, I can't.
Yeah, when you're just trying to find the
This is still on the instant.
Oh, I use HF.
For omega 2, this is in waters or air?
Air.
do you have a agent? Oh,
It's just to.
low.
Hey, for the 5, what omega do you use in the formula? Omega 1? For the relative humidity, which omega do you use?
Omega 1. If you use omega 2, you get 100%.
Maybe you should check.
Yeah, you should get like 47%.
Yeah, that's what the chart says. We have wrong.
Maybe like maybe.
So what is your, sorry,
So our HG.
this is these are the omega 1 and omega 2 values.
Which pressures do we use?
Which pressure for P2?
They're for P and PG, for relative humidity.
P is just the regular pressure, atmospheric pressure, and P sub G is the P sub G at PG1 at 1.
So it's PG1.
Yeah, run it down as PG.
You were in that program in middle school, elementary, no,
So what do you?
It's not sure right now.
Yeah, he has PG. I just.
I'm a little surprised.
It's a key
Pressure. Yeah, it was a bunch of pressure.
The V equation? Yeah.
On PG, that's what it gives us. PG.
I got 62 versus.
That's still way too high. Wait, 62 for which one?
For relative humidity on the.
Back, right?
We did all 3.
Yeah, half of those.
You still calculate all 3.
Okay, so,
82
that's too high.
for the Thermo pen change.
Too high.
That's what I was
Too high.
thinking.
Okay, so we'll look at these in a little bit more detail, but we need to get on with the psychrometric charts. So now we're going to use these same values that we found the wet bulb, dry bulb temperatures, and learn how to use these psychrometric charts. And I think you'll see that if your values are off significantly, then there's a problem in your calculation somewhere. So we'll address that and look at it. Here. Okay, so as I pointed out previously, we can see several different things on the psychrometric charts. All of these property values are available on there. So if you know dry bulb temperature and wet bulb temperature, then you just intersect those 2 points and look up the rest of the values. Or maybe you know dry bulb temperature and specific humidity, or relative humidity, or specific volume. So whatever 2 you know, you use that to fix the point, and then we look up the rest. If you are trying to determine your saturation temperature or your dew point temperature, if you look at this psychrometric chart, it's just there. If you look at the psychrometric chart, and let's say, okay, so let's just say, for example, that you were right here on the psychrometric chart. You wanted to figure out your saturation temperature. You would draw a line directly horizontal over to the axis to find out what it is. So in this case, if this is 15 and this is 20, halfway between the two is about 17.5. So this one is going to be maybe like 18.7, something like that.
Why wouldn't you follow the direction of the lines?
Which lines?
The enthalpy lines, like how they're all diagonal. It's like you'd follow it.
Follow like that.
Yeah, yeah.
Well, if you wanted to determine your enthalpy, then you would follow those lines.
Oh, sorry.
Yeah, so, but to find the saturation temperature, you go directly horizontal. To find your dry bulb temperature, you go perpendicular down to the lower axis. if you want to read your specific humidity or the humidity ratio, then you follow that line to the far right. And you remember when we were doing dew point problems, and we're going to do an example of that as well, that we said, okay, you know, overnight our temperature is decreasing, so that would be an example of what would happen for a humidity problem, that we're at some relative humidity, let's say 40%, and overnight as our temperature decreases, our humidity, our relative humidity increases, but our specific humidity stays the same until we get to 100% relative humidity, and then stuff starts condensing out. So if you were at any point on this chart or on this diagram and you wanted to figure out what your dew point temperature is, all you have to do is follow the line over to the horizontally to the saturation line, and then you can determine your dew point temperature, or the temperature at which the liquid will start condensing out of your material or your fluid. Does that make sense? You look puzzled, Chris.
Yeah.
Okay.
Which ones are the graduations for saturation temperature?
So we use the dotted black lines.
You use the dotted black lines for what?
19 degrees Celsius, right?
For 19 degrees. What are you talking about? On your AccuRite thermometer?
Yeah.
Okay, so let's just do an example of that, right? So let's take the AccuRite thermometer where our dry bulb temperature is 27 degrees. So if we start out at 27, this is 25, 26, 27. That's a dry bulb temperature of 27 degrees. And then our wet bulb temperature is 19 degrees Celsius. So we look at the wet bulb temperature line, so that's 25, that's 20, 19 is right here. So that's where they intersect, and you can see that it's in between 40 and 50%. It's a little bit closer to 50 than it is to 40. So if we were to determine our relative humidity using the chart, it should be around 47%, which is what we got with, some of us got with calculations.
We fixed it.
You found it? You found your error? Okay. Now if we wanted to know, okay, that's our dry bulb temperature, that's our wet bulb temperature, at what temperature, if we were to hold everything else constant, would fluid start condensing out of this air? So overnight, if the overnight low goes below, it's like 14.8 degrees Celsius, then we'll have dew on the ground.
Okay.
So given this particular relative humidity and the temperature, the dry bulb temperature, then we can figure that out.
I was just confused what that horizontal line was, but it's your dew point.
Yeah, it's your dew point, and it's also your specific humidity. Because the amount of moisture in the air isn't changing, the total volume or the total mass of moisture in the air is not changing. What changes is the fluid's capacity to continue to hold moisture. So if the temperature decreases, then your relative humidity will increase just because your air has less ability to hold moisture. There's still the same amount of total moisture in the air, but your air can't hold it anymore, so it will start to condense out if the temperature goes below the dew point. Okay, so let's do some examples of this. I don't think we have time to fill out this whole chart. So here's the answers. But let's just do, you have to go watch the video to find the answers, and it's like an hour into a boring video. Okay, so let's do a couple of examples. This one is a greenhouse that must be maintained above 60 Fahrenheit and 50% relative humidity for the tropical plants inside to stay alive. So if we go to our psychrometric chart using SI or English units.
This one seems a little spread out.
Okay, so there is my chart that erased some stuff on here. Okay, so 60 Fahrenheit and 50% relative humidity. So if our dry bulb temperature is 60 Fahrenheit and our relative humidity is 50%, so we go to our chart and we say, okay, we need to be at a greater temperature and a greater humidity than that, which would mean that for our greenhouse to keep the plants alive, we have to be somewhere in there. So we have this temperature equation that relates the indoor temperature to the outdoor temperature. And so we want to use the psychrometric chart to determine if the outside temperature is 20 Fahrenheit and the specific humidity is 0.008, will the plants thrive? So the first thing we do is calculate the inside temperature. So it's negative 0.01 times the temperature outside squared, which is 20 Fahrenheit squared, plus 1.68 times 20 squared, not squared, plus 34.8. So we find that is equal to a temperature inside the greenhouse of 64.4 degrees Fahrenheit. So now we can use this value, the 64.4, and the 0.008 pounds water per dry air, and go back to our chart. So if our dry bulb temperature is 64.4, so it's going to be somewhere like around there, and our specific humidity is 0.008, so we just follow that up, and we see that we're within the safety region for our greenhouse, so our plants will be okay. So I can change that. I can change that to be a different color. So we determined the safe region, and then we found that our point lies within there, so we're good.
So when it says outside temperature is 20 degrees, is that our dry bulb?
No, the outside temperature is used to calculate the indoor temperature. So there's some relationship between the greenhouse and its ability to maintain heat when the temperature is a certain. I just made up this equation, but
The
it may happen.
the 0.008, you said the saturation line is the same thing for your specific humidity, right?
No, the saturation line is not the same thing. Saturation line is
Right.
here,
Right.
but when you're at a certain point and all you're doing is increasing or decreasing the temperature, you're going to follow a line of constant
Okay.
specific humidity, because the amount of moisture in the air is not changing unless you start condensing or adding moisture to it. So if your process is just a temperature increase or a temperature decrease, then you would just follow along that line. So your relative humidity will change as you move through that space, but your specific humidity remains constant unless you're adding or removing moisture. Any other process, if you're just adding or removing heat but not changing the moisture content, then you stay constant on that specific humidity line. Okay. The temperature and relative humidity of air at 9 p.m. on a summer night is 80 Fahrenheit and 45% humidity. Okay, so let's go to our chart, and we find in the, this would, going up. Okay, so 80, oh, I was on the right one. 80 Fahrenheit and 50% humidity. So it's the intersection of this 50% humidity and 80 Fahrenheit is where we find our point on a summer night. Now the question is, if the temperature in the morning is 65 degrees Fahrenheit, will there be dew on the grass? Okay, so if we're assuming that it's just atmospheric pressure and all that's happening is the temperature is decreasing to 65 degrees Fahrenheit, then we can see that we'll end up right here. So will there be dew on the grass in the morning? No, right? We haven't reached the saturation point. So our humidity has increased to 80%, a little bit over 80%, but we're still not to 100% humidity, so there will be no dew on the grass in the morning. Okay, so we start out at 80, and then we follow a line of constant specific humidity until we get to 65.
So if it's like 55, there would be dew.
Yeah. Yeah, and in many cases, even if the overnight air temperature is like, 65 or something like that, sometimes the ground temperatures are cooler depending on what's going on. So you may have dew or localized dew in certain areas. But
So the saturation temperature has to be lower? than the dry bulb temperature? Or do you do?
No, your dry bulb temperature would have to be below the saturation temperature. So once you get past this point, you would then continue along the saturation line and you start losing some of the humidity from your air. So let's just say that happened. Let's say that instead of going to 65 Fahrenheit, we went down to 45. So you would follow a line of constant specific humidity because your humidity is remaining constant. All you're doing is decreasing the temperature. But once you reach that saturation point and some of that dew condenses on the ground and is removed from the air, now you're following the saturation line where you're still at 100% humidity, but some of that moisture is leaving the air, so your specific humidity is decreasing.
So it's like a balancing act. It tries to equal, as it hits 100, if you keep dropping it, it lowers the other one going this way to maintain it.
Because the specific humidity is the ratio of the mass of the water to your air, the mass of the air. So if you're losing water to dew, then that ratio is decreasing. So you're still at saturation, you're still losing water, you're still at 100% humidity, and as you lose water until you reach some equilibrium point where the temperature no longer decreases, but you're still at 100% humidity. Okay. Sample 4. We have 15 kilograms of dry air at 20 degrees Celsius. And we're going to humidify it by adding water vapor at a constant temperature of 20 degrees Celsius. So we want to use the psychrometric chart and determine the maximum amount of water that can be added at that temperature. Okay, so 15 kilograms of dry air, and we want to figure out what's the maximum water that we can add at that temperature. So now if we look at our psychrometric chart, and we need to go back to the Celsius one. So we have 20 degrees Celsius and dry air. So we're starting out at 20 Celsius and dry air has 0% relative humidity, 0 specific humidity. There's no water vapor in the air. What we want to figure out is how much liquid can we add to the air before it becomes saturated. So now we're following a vertical line up to the saturation line. So by adding water to the air, we're going to increase our specific humidity and our relative humidity at the same time. So we want to figure out where we are when we're at 100% humidity. Okay, so if we go to that point to the saturation line at 20 degrees Celsius, and we read this over here, that we're at 15, approximately 15, omega is equal to 15 grams per kilogram, or 0.015 kilograms per kilogram, right? Okay, so we found from the chart that omega will be 0.015 kilograms of water per kilogram of dry air at the saturation point. We also know that omega is equal to the mass of the vapor over the mass of the air. We know our mass of the air is 15 kilograms, so the mass of the vapor is equal to omega times the mass of the air, which is just 0.015 kilograms of H2O per kilograms of dry air, multiplied by 15 kilograms of dry air. So we can add m sub v equal to 0.225 kilograms of water. That's the maximum amount of water we can add at that temperature before it just starts condensing out. That's the maximum amount of water that the air will hold. So we can't add any more than that. Okay, so all of these problems that we did using the psychrometric chart, you could also do, and I've shown in the notes in the lecture examples that you can calculate those all by hand as well, using the same equations that we've used for all of the other problems. So it's equivalent. One is more approximate, but it's way quicker. So psychrometric charts allow you very quickly at a glance, instead of having to do all of those hand calculations that you guys were doing back there to find the relative humidity, you can just plot the 2 points on your graph and eyeball it or figure it out from there. So depending on how accurate you need to be, that may be sufficient for running your experimental design or figuring out whether your plastics are going to work during the molding process. So Austin, share with the class what your work had you do just yesterday.
I work at an injection molding plant as an intern, and when the temperature changes really bad, our parts warp. So my boss had me figure out the humidity in the air to see when the parts would warp and what we can do to stop that from happening. We need to make a controlled environment or not.
So real life application, right?
Yeah.
And it happens just at the right time.
Yeah, it really did. I would have done a lot of Googling.
So, it's good to know how to do this. It may never come up in your engineering career, but it may come up a lot. If you're, I think everybody in here is mechanical engineers, but civil engineers, if they need to pour concrete, they need to know the humidity of the air to determine cure times and strength and things like that. So, if you're dealing with electronics, you need to know humidity, because that affects cooling. Or if you're, doing some other materials testing or processing, that it may be very important.
Wasn't that like a really big deal when they were building the Burj Khalifa, because they were like having weather inside it when, like
Oh, it
before they
has,
shut
yeah,
it?
it has like its own microclimate in the upper. So, yeah, wind, sand, humidity, all of those played a huge role in that building. Pretty significant undertaking. And now they want to make one even taller, so good luck with that. All right, any questions? Hopefully you started on the homework. It's pretty straightforward, easy to do, but again, be careful which values you use. Like, what is the saturation pressure? What's piece of G? What is it?
Oh, it's P.
Not just P.
The P in the table, whatever that is.
Okay, saturation pressure, right? So make sure that you use the right values, and if you have any questions, send me an email. And see you on Tuesday. Homework is due on Tuesday.
So, no Charlotte, number one candidate. I'm one.